Hello friends, I welcome you in lecture number 5 on residue integration of real integrals. In this lecture we will discuss one more example on evaluation of improper integral by residue theorem. But in this lecture, to calculate residues of a function, we are not going to use that earlier result. We will be using this result for calculating residue of f of z at a point z0. As we know that if we can write our function f of z in this form, phi of z over z minus z0 raised to m, where this phi of z is analytic at point z0 and value of phi at z0 is non-zero, then f of z has a pole of order m at z0 and residue of f of z at z equal to z0 is given by m minus 1th derivative of function phi at z0 divided by m minus 1 factorial. So far we have used this result to determine residues of a complex function. Now every time it is not comfortable to use this result for calculating residues. So for that we have another result. So first we discuss what is that result. Suppose my function f of z is division of two functions, say p and q, where p and q both are analytic at some point, say z0, and suppose value of p at z0 is non-zero and z0 is a 0 of order 1 of this function. That means q of z0 is 0 and q dash at z0 is non-zero. I repeat again, suppose f of z is division of two functions, say p of z and q of z, where functions p and q both are analytic at z0 and value of function p at z0 is non-zero and q of z0 equal to 0, q dash z0 is non-zero. This means z0 is a simple 0 of function q. So if these two conditions are satisfied, then z0 is a simple pole of function f and residue of f of z at z equal to z0 is given by value of function p at z0, which is non-zero, divided by value of first derivative of q at z0, which is also non-zero. So we are going to use this result to calculate residue in this problem. So we come back to our discussion. We are discussing lecture number 5 on residue integration of real integrals. So first I have written this theorem: let two functions p and q be analytic at z0 if p of z0 is non-zero, q of z0 is 0 but q dash at z0 is non-zero, then z0 is a simple pole of the quotient p over q and residue of p over q at z equal to z0 will be equal to value of p at z0 divided by value of q dash at z0. So we will use this result in calculating residues for this example number 4. Now we start evaluating this integral. Here answer is already given. We have to show that value of this improper integral is pi over 2 root 2. So first we denote given function by fx. Let fx equal to 1 over 1 plus x raised to 4. So as we know, here degree of numerator is 0 and degree of denominator is 4. So degree of denominator is strictly greater than 0 plus 1, that is degree of numerator plus 1, and this x raised to 4 plus 1 is non-zero for every x belongs to R. So this shows that given improper integral is convergent, and we can apply Cauchy's residue theorem to evaluate this improper integral. So first we write the corresponding complex function. We replace x by z, so we have f of z equal to 1 over 1 plus z raised to 4. Now we find out the points at which 1 plus z raised to 4 becomes 0, because f of z is a rational function. So poles of f of z will be equal to solution of this equation, z raised to 4 plus 1 equal to 0. So we solve this equation, z raised to 4 plus 1 equal to 0. So for this we rewrite this as z raised to 4 equal to minus 1. This gives me z equal to minus 1 to the power 1 by 4. So I require fourth root of minus 1. So for that we recall that result, that if I have z equal to polar form r into cos theta plus I sin theta, then nth root of z is given by this formula, r to the power 1 by n cos theta plus 2k pi divided by n plus I sin theta plus 2k pi divided by n, and this k runs from 0, 1, 2 up to n minus 1, and this r is nothing but absolute value of z, theta is nothing but one value of argument of z. So here we are interested in the fourth root of minus 1. So first we find out modulus of minus 1. So modulus of minus 1 is obviously 1, and minus 1 is on negative x-axis. So if we measure the angle with positive x-axis, this is positive x-axis, then this angle is pi, so we have theta equal to pi. So in this case r is 1 and theta is pi, and n equal to 4 because we are interested in the fourth root. So we substitute all these values in this formula, and we will be able to find out minus 1 to the power 1 by 4, which is equal to r raised to 1 by 4. Here r is 1, so 1 raised to 1 by 4 is 1, and here we put theta equal to pi and n equal to 4. So we have pi plus 2k pi, theta is pi plus 2k pi divided by n, n is 4, plus I sin pi plus 2k pi divided by 4, and here k runs from 0, 1, 2 up to n minus 1. So here n is 4, so we have to go up to 3. So therefore minus 1 raised to 1 by 4 will be equal to this I can rewrite as e raised to I times pi plus 2k pi divided by 4 using Euler's formula. K is from 0, 1, 2 up to 3. Okay, we know that we can write e raised to I theta is nothing but cos theta plus I sin theta. So I am using this formula here, cos theta plus I sin theta is e raised to I into theta. So therefore minus 1 raised to 1 by 4, this we can rewrite by taking pi common. So we have pi I divided by 4 times 2k plus 1. K is from 0, 1 to 3. So for different values of k, we will have different roots of minus 1, different fourth roots of minus 1. So suppose I put k equal to 0 and I denote corresponding root by z0. So for k equal to 0, I will get, if I take k equal to 0, I will have 1 here. So I obtain pi I divided by 4 for k equal to 0. For k equal to 1, corresponding root is denoted by z1. So if I put k equal to 1 here, I will have 2 plus 1 3, so I obtained 3 pi I divided by 4. Similarly, I write here for k equal to 2, I denote corresponding root by z2, and here if I put k equal to 2, I will have 2 into 2 4 plus 1 5. So I have e raised to 5 pi I divided by 4. And for k equal to 3, corresponding root is denoted by z3, and 2 into 3 6 plus 1. So here I have e raised to 7 pi I divided by 4. So these are the fourth roots of -1, and that are the values of z for which this equation is satisfied. That means those are the poles of f of z. Now we are interested in the poles in upper half plane only. So we can see this e raised to pi I by 4 and e raised to 3 pi I by 4. Here angles are pi by 4 and 3 pi by 4. So both are less than pi. Pi by 4 is strictly less than pi, and 3 pi by 4 is strictly less than pi. So these two roots are in the upper half plane, and here 5 pi by 4 and 7 pi by 4, both the angles are greater than pi. So they are in the lower half plane. So only z0 and z1 are in the upper half plane, and z2 and z3 lie in lower half plane. So which are not of our interest. So we will concentrate on z0 and z1, that is e raised to pi I by 4 and e raised to 3 pi I by 4. So we will calculate residue of f of z at these 2 points only. So we can write that f of z has simple poles at z0 equal to e raised to pi I by 4 and z1 equal to e raised to 3 pi I by 4. So to decide whether these two are simple poles, we can use that result. Here our f of z is 1 over z raised to 4 plus 1. So if we compare with p by q, we have pz equal to 1 and qz equal to z raised to 4 plus 1. So pz is constant function, so we can see p of z0 is non-zero, and similarly p of z1 is also non-zero. Value of p at z0 and z1 both is non-zero. Now qz is z raised to 4 plus 1. So we have shown that this q of z0 and q of z1 are 0, because z0 and z1 are zeros of z raised to 4 plus 1. So q of z0 and q of z1 both are 0. And if we check for q dash, so q dash is going to be 4 into z raised to 3. So if we put, first we put q dash at z0, then that is going to be 4z0 raised to 3. Now z0 is nothing but e raised to pi I by 4 raised to 3. So that is going to be 4 times e raised to 3 pi I divided by 4. And if you simplify this, you will obtain that it is non-zero. 3 pi I by 4, that is pi minus pi by 4. So we can simplify this as cos 3 pi by 4 plus I sin 3 pi by 4. and if you simplify this you will get non-zero complex number. So this shows that both the poles z0 and z1 are poles of order 1. So I have written directly that f of z has simple poles at z0 and z1, and we can write directly, it is obvious here, so no need to show all these things, this is just for understanding. So now we calculate residue of f of z at z0 and z1. So now we will use this result, that residue of pz over qz at z equal to z0 will be equal to p of z0 divided by q dash at z0. So first we write here p of z is 1 and q of z is z raised to 4 plus 1. Therefore q dash is going to be 4 into z raised to 3, and residue of f of z at z equal to z0 will be equal to value of function p at z0 divided by q dash at z0. P of z is 1, so therefore p of z0 is also 1. Q dash z is 4z cube, so this is going to be 4 into z0 raised to 3. Now what is z0? Z0 is e raised to pi I by 4. So we have e raised to pi I by 4 to the power 3. So that is going to be 1 by 4, 1 over e raised to 3 pi I divided by 4. So this is, again we can rewrite this as e raised to minus 3 pi I divided by 4. So this is residue of f of z at z equal to z0, that we denote by say b1. Now we calculate residue of f of z at z equal to z1. So same formula we are applying, residue of f of z at z equal to z1 will be equal to value of function p at z1 divided by value of q dash at z1. P of z is 1, so p of z1 is also 1. Q dash z is 4 times z cube. So here we have 4 times z1 to the power 3. Now z1 is e raised to 3 pi I by 4. Let me check. It is e raised to 3 pi I by 4. So here we put e raised to 3 pi I divided by 4 to the power 3. So this is going to be 1 by 4 and 1 over e raised to 9 pi I by 4. So if we rewrite this, we have e raised to minus 9 pi I divided by 4, and if we wish we can simplify this. We can rewrite this as e raised to minus 9 pi I by 4 can be rewritten as, if we use the formula, that e raised to minus I theta is nothing but cos theta minus I sin theta. Then we have cosine of 9 pi by 4 minus I sin 9 pi by 4. Now I can rewrite pi by 4, 9 pi by 4. 9 pi can be written as 8 pi plus pi divided by 4 minus I sin 8 pi plus pi divided by 4. So we have to simplify all these things. If we divide 8 pi by 4, we have 2 pi and plus pi by 4. So angle is in the first quadrant, 2 pi plus pi by 4. So if we are in first quadrant, all the angles are positive, so we have 1 by 4 times cosine of pi by 4 minus I sin pi by 4. And I think I should simplify b1 also. Okay, so we simplify b1. Here b1 can be rewritten as, we write here b1 is 1 by 4 times e raised to minus 3 pi I by 4, that we can rewrite as cos 3 pi by 4 minus I sin 3 pi by 4. Now this angle 3 pi by 4 can be rewritten as pi minus pi by 4. We can see this is going to be 4 pi minus pi, that is 3 pi by 4. So we replace 3 pi by 4 by pi minus pi by 4. Cosine of pi minus pi by 4 minus I sin pi minus pi by 4. Pi minus pi by 4 means we are in second quadrant. In second quadrant cosine is negative, so we have minus cos pi by 4, and sine is positive, so this is going to be sin pi by 4. So this is our b1. So we have simplified b1 and b2. So now we can use Cauchy's residue theorem. So here I have written, by residue theorem we have integral minus infinity to infinity fx dx will be equal to 2 pi I times b1 plus b2. Now in b1 and b2 1 by 4 is common, so that I have written outside, and now I consider remaining portion of b1 and b2. So in b1 1 by 4 is taken common, and we are left with minus cos pi by 4 minus I sin pi by 4. So that is minus cos pi by 4 minus I sin pi by 4, and plus b2 1 by 4 is taken common, and we have cos pi by 4 minus I sin pi by 4. So we write cos pi by 4 minus I sin pi by 4. So we can see this cos pi by 4 will cancel out, and this is 2 times minus I sin pi by 4, and here we write one more step, 2 pi I into 1 by 4 into minus 2I sin pi by 4. So this 4 will cancel out with this 2, and we have pi I into minus I, that is minus pi I square, and sin pi by 4 is 1 over root 2, and if we put I square equal to minus 1, we have positive sign, and we have pi divided by root 2. So this is the value of this improper integral from minus infinity to infinity. Now let me rub this. Now our function is 1 over x raised to 4 plus 1, which is even function. So this integral from minus infinity to infinity can be written as 2 times 0 to infinity fx dx, because fx is even function. So we have pi over root 2, and we have fx equal to 1 over x raised to 4 plus 1 is even function. So therefore integral from 0 to infinity, we take these two on right hand side, and we obtain that integral from 0 to infinity fx dx is going to be pi divided by 2 root 2. And finally we substitute what is our fx, it is 1 over x raised to 4 plus 1. So value of this integral is pi over 2 root 2, that we have shown using residues theorem. So in this example, what is new thing is, the new thing is we have used another method of calculating residues. So for that we remember this result, that if two functions p and q are analytic at point z0, if p of z0 is non-zero and z0 is a 0 of function q of order 1, then residue of pz over qz at z equal to z0 is given by p of z0 divided by q dash z0. And here to find out roots of denominator, we are using this formula for calculating nth root of complex number. So this is all about this session. I hope you like it. Thank you very much.